Thank you for the introduction. My name is Briya and I'm a PhD student in physics at Khalifa University. Today I will talk about deep learning based metal artifact reduction using conditional generative adversar networks. In medical imaging, if there is, particularly in computer tomography, if there is any kind of metal objects present within the body, it will distort the images very. So it's called metal artifacts, and we can see in this image, it's the image of a hip implant with barium cement. It was, the purpose of this imaging was to check if there is any bone fragment were extruded from the femoral fracture side, but as you can see that there is indistinguishable attenuation values between the barium and the bone, and also the soft tissue information is lost due to the streaks. So there are some causes of metal artifacts. The main causes are streaking, beam hardening, scattering, photon starvation, partial volume effect, and also if there is any dense material is present during the scan. So in short, metal artifact in CT imaging often lead to non-diagnostic images, repeated scans, increased radiation dose, and uncertainty in the patient care. Here are some main images from the causes of metal artifact reduction. The first image is showing the streak artifact, that is basically the bright and the dark streaking that comes due to the beam hardening and the photon starvation. Beam hardening when low energy photons attenuated more as compared to the high energy photons, and photon starvation when there is insufficient number of X-ray photons reach to the detector. So these are some main causes of metal artifacts, and as we know, there are many traditional ways for the metal artifact reduction, but still they are facing many challenges in when we have complex variations in the artifact. So this challenge calls for the development of more adaptive algorithms. So nowadays deep learning based metal artifact reduction is working more accurately as compared to the previously available traditional MAR algorithm. So for our deep learning based MAR, we use the training dataset provided by AAPM, with collaboration with GE Healthcare and First Imaging. So we use the training dataset consisting of 14,000 cases, and each cases have images and the sinogram, and we work in the image domain. So the types, they use 5 types of metals: titanium, steel, gold, amalgam, and cobalt. And the dataset they provided us have corrupted images having metals and with artifacts, labels without metal, without artifacts, and the metal only mask. So for the supervised deep learning, because that gives us more accurate results, we use make our ground truth images by using the labels and the metal only mask. So if I will go through the framework of our deep learning model, we use the CGAN model, that is basically consists of 2 individual networks, generator and the discriminator. For the generator is trained on corrupted images and the target images to produce the artifacts-free images, and the purpose of the discriminator is to just classify between the generator, between the output images and the target images, what is the loss between them. So if I will go straightforward go to the results, so for the validation of our deep learning model, we are showing the worst results and the best possible results. If we just focus on this images, so input image have many artifacts, and the metal is totally distorting the images. But in the output image, we can see that the model is able to retain the properties of bone and the soft tissues. And similarly, if we look at any image from the head, In the input image, we have metals and many artifacts, but in output image, we can clearly see that. So we can conclude that our model is performing very well on these type of sphere artifacts. And for more demonstration, there is another image, and in the output image, there is no distortion, and model retain the bond and the structure properties. For the more evaluation, we tested our model for some evaluation parameters like root mean square error that actually checks the attenuation profile, and it should be low, and we got like a very low value as compared to the already published deep learning models. For structure similarity, we got the best possible result, that is close to 1, and the peak signal to noise ratio that basically check the image quality. So for all the images, we have image quality greater than 40. For more in the pixel intensity distribution, we check the histograms, and the output image shows the highest peak, and it shows that there is no presence of artifacts, and all the most of the pixel values lies within the same energy range. So we have also generated the graphical user interface for this deep learning model, and it can easily just in few seconds, if we will provide the input image, it will give the output images. So in conclusion, our model is have very good results in terms of all the evaluation parameters, and in the future works, we are aiming to optimize our model for the multi-energy photon counting city.
Great, thank you. Done on time.